So good morning, I am Krishna Kumar from Krishna's classroom. Today we look at the so-called linear functionals defined over a vector space. Okay. So we have, to start with, we have a vector space V. Is a vector space over a field F of dimension dimension. Now we will be considering only finite dimensional vector spaces here, although the concept of linear functions can be defined even on infinite dimensional vector spaces. Now we begin with the definition of a functional definition. We begin with the definition of a function. What is a functional? A functional is a function from V to F. So a functional on V is a function from the important factor is that the domain is the whole of vector space in this case, and the range is the associated field. Let's give some examples. We take V to be R, our favorite model. Okay. Now let X belong to R3. Then X is equal to X1 with respect to the standard basis. The standard basis E1, E2, E3, or even with respect to any basis. It doesn't matter. No. Now we define space. And you know that this is a scalar. Therefore, for every x, it is mapped to the second component of the vector. So it's a field value function defined on R. The field here is R. So real value function defined on R3. Therefore, y is a function. Second example, a number of examples. Same notation, x defined like this. We write y of x, we define as the positive square root of x1 square plus x2 square plus x3 square. Now you know that this is exactly the length of the vector. So the length of the vector, or which you call the L2 norm of the vector, or the Euclidean norm of the vector, is a function. B equal to R3, again the same notation. We define y of x a1 x1 plus a2 x2 plus a3 x3 for every x. Where a1, a2, a3 is a fixed vector in such an order to a1, a2, a3. That is the scalars a1, a2, a3 are given, and you work this out for each x. Then this is a real number. Let's see this. This is again fourth example. We take V2 and this is a polynomial of degree less than or equal to 2, including 0. That is a vector space. It's a vector space of dimension 3. Then we define y of this is again gives you a real number, therefore it's a function. Into R. So we define y of this you define as you know that this integral exists, there is no problem, it's a polynomial. Okay. It's again a continuous function, this is again a continuous function, therefore the integral exists, there is no problem. Next example, we take on V, on any V, define this is also a, that means every vector is mapped to the scalar 0. This is a again a function. Now we go on to be more specific. We consider a certain class of functions which in a way has a structure that goes with the structure of the linear space. This is linearity. So we consider a special class of linear spaces, a special class of functionals, which we call a linear function. So we now, if you want an example of a map which is not a linear function, not a function at all, then you write fx equal to x. Except in the case when it is equal to f. Right? So that's the reason. The linear function. A function from following are true. Y of B is 1 and Y of Cx is equal to C times x belonging to. We call this a linear function.
Now one can easily verify that.
The examples 1, 3, 1, 3, then the fourth one, yeah, 4, and then 6 are linear. The other two are not linear functions. They don't satisfy these conditions. Check which condition is true. Okay. So we have defined what a linear function is. So we are talking about linear maps from B to F. And you know that B is a linear space over F. F is also a linear space over F. And we are now looking at maps from B to F which has the special property called linearity.
So we expect this collection of objects also
to acquire certain nice properties. Now let us give a notation. So let B prime denote all y belonging to all y such that y is a linear functional on B. So the set of all linear functions on B is denoted by B prime. Now the first theorem that we do is that B prime is a statement I made. That nice structures are inherited from the domain as well as the range, as well as from the linearity properties of F. Okay. So let us prove this. So what you have to prove, if y1 and y2 belong to B prime, then we have to show that y1 plus y2 of C times. But that's obvious. That's how the functions are defined. Okay. We talk about the sum of two functions and this is how you define the sum of the two functions and the scalar multiple of the function. What do we want to show? We want to show that if y1 and y2 belong into, then let me slightly. Okay, this is how y1 plus y2 and cy are defined for every y1, y2 belong to B prime and C belonging to F. This is the definition. Now what we assert is that if y1 and y2 belong to so what do we have to do? We have to show the following. We have to prove this y1 plus y2 of x1 plus x2 equal to and C times this is what you have to verify. So let me just do one thing, one of them, and the other is in a similar way you can do it. So let us work. So let us start the proof of this way. So by definition, see, y1 plus y2 of x1 plus x2. What is this? This we have defined what is the sum of two functions. Now this is equal to y1 of x. Okay. Now we apply the fact that y1 and y2 are linear. So that's equal to y2. Therefore, this is equal to, see, we interchange these two, so you see that this is actually y1 plus y2 of x1 plus, once again applying the differential. I have skipped one step in there. Okay. Similarly, one gets y1 plus y2 cx is equal to y1 cx plus y2 cx. y1 and y2 are linear, therefore this is equal to c times therefore you see that y1 plus y2 similarly one proves that Cy is linear, or at least C belongs to here. It's just similar steps you have to do, but you have to do this shortcut. So that's about, so both, if y1 and y2 belong to V prime, then y1 plus y2 Cy are linear functions. Now we have to go beyond that. We have to show that this is essentially a linear space. For a linear space, you see that these two, the sum of two elements in V prime is in V prime. A scalar multiple of an element in V prime is in V prime. What more you have to show? You have to prove the following. So y1 plus y2 plus y3 equal to so this is quite easy, because you know that y of x equal to z of x if, or y equal to z if and only if y of x equal to z of x for all x. We have to use that. So one verifies this. Then similarly, you have y1 plus y2 equal to y2 plus y2. This is true for right? Now you have the zero function. Note that zero of x defined as 0, x belongs to V is a linear function, is an element of V prime. What do you have to show? This is a linear function because what you have to show is that 0 of x1 plus x2 equal to 0 of x1 plus 0 of x2, 0 of cx equal to c times 0 of x. I mean, they are trivial. What more you have to show? You have to show that 0 is the identity element. Now, linear function. And further, 0 of y plus 0 is equal to 0 plus y. Again, verify it on arbitrary x belonging to V. Okay, so that's the method, and that's trivial to verify. Use the definition of 0. Now, given y belonging to V prime, there exists a linear function. Minus y belonging to V prime such that so there are a few things here. But to show that given y, minus y is a linear function. You can go back here that given y, cy is a linear function. Therefore, if you take c to be minus 1, then it's a linear function, or you can directly. So that's the definition of minus 1. Okay. So note minus y defined as minus 1 into where minus 1 belongs to the field. That is the additive inverse of the multiplicative identity 1, whatever that may be. Okay. So now you can verify, one can verify all other conditions for V prime to be a linear function on V. Not to be a linear function. That's the verify that. So you know all the conditions that are required, something like say a plus b times y a y plus b y, and AB times y equal to A of y. 1 of y equal to y. 0 times y equal to 0 linear function, etc. So that you have to verify. So this will be property. So A of y1 plus y2 equal to A into y1 plus y2 equal to ay1 plus ay2, etc. So all these properties are to be verified and they are very quite easy. Each time proving whatever you write is well defined and is proved that it is an element of B prime. Thus, B prime is a linear space. So, given B, a finite dimensional vector space, you have a new linear space associated with B consisting of all linear functions. Okay. This is called the dual space. You must therefore, the natural question, if you have a linear space, is what we say about the dimension of the linear space. Okay. Second fact is that this is not an arbitrary linear space. This is a linear space that has come out of B or very closely related to B. Therefore, you would also like to ask the question, how is this, the dimension of this related to the dimension of B? So there are two questions. B prime. That's one question. How is it related to the dimension of dimension? These are the two questions that immediately come to your mind. Whenever you come across a linear space, one of the first questions that you ask is there a, or can you say something about the dimension of this space? It has come out of a special circumstance, like in this case it has come out of B. Then you also ask how this is related to the dimension of the known vector space. These are the natural questions. So you can go one step further. One. Can one construct a basis B prime? Because if you answer this question, then immediately the other things are answered. What is the dimension of B prime? And it will be clear from that what is going to be, how it is going to be related to the dimension of B. So essentially, if you try to answer this question, the third question, then the other two are automatically resolved. Okay.
So let us, so what is the information that you have? You know that the dimension of V is n. That is where we started. Therefore, there exists a basis for V. Okay. Now, we first make an observation. The observation is this. Suppose you have a basis for V. Then if you specify a linear functional on the basis, by which you mean the evaluation of the linear functional on the elements of the basis, that fixes up the linear function. So we make a statement about it in the form of a theorem. A linear function on V is completely defined its values defined by the values takes on the elements of the basis. It's a very useful list. Okay. Once you know the values of what, suppose you start with a y belonging to V. It is enough to say what values y takes on x1, x2, etc., xn, where x1, x2, etc., xn is a basis for V. Then the linear functional is completely determined. So let us do this. Let script x basis for, you know that every basis consists of n linearly independent vectors in V. So V xi's are okay. Let y belong to say linear function or not. Then y x1 y xn are that is the evaluation of y at x1, x2, etc., xn are elements of. So we want to compute from this the value of y at any x. Image of any x belong to V let us do this. how do we work on this? So let X be an arbitrary element of V. Then X is equal to C1 X1 plus Cn, where C1, C2, etc. I. Ci's are uniquely dependent. This is the unique representation of X in terms of the basis x1, x2, etc. xn. In fact, I should say the ordered basis. I don't want to change that order for this discussion. Okay. Now, what about yx? Y of x is equal to y of and this bilinearity is C1 therefore, if you know yx1, yx2, etc., yxn, that means the evaluation of y on the ordered basis x1, x2, etc., xn, then you completely know this number. That means the image of x is fixed. Okay. Clearly, y is and y is determined if y x1 so we see that for any arbitrary element of V, yx can be computed for a given y, provided you know yx1, yx2, etc., yx. Now this is the power of linearity. Okay, it's because of say y is linear that we are able to do this. Okay, right. Because we have used linearity here from this step to this. Therefore, a linear function is not a linear function on V is completely dependent by assigning specific values for y at x1 if you specify yx1, yx2, yxn, then y is completely. Now we shall make use of this. Okay. So the next step is to prove our theorem. So we have done only a that, right? So we use this to construct a basis for B prime, if possible. So now what do we do? So we have in ordered basis. This forms a linearly independent set of vectors in V which span the whole space. That's why you call it a basis. And we also keep it ordered because we don't want to interchange this or mess up the whole thing through a permutation. Just once you start with x1, x2, etc., etc., that order is preserved throughout the discussion. Now define yi by yi of xj equal to delta it. Delta it is the Kronecker delta. In particular, you see that you look at yi. What is the definition of yi? Yi at x1 equal to delta I1 if So you see that this is yi is at x1 is 0 if I is not equal to 1. Only yi evaluated at xi is equal to 1, all other places its value is 0. Okay. So this is being delta. Therefore, yi is fixed because we know the evaluation of yi at x1, x2, etc. So now yi's are well defined. These are all linear functionals over V. Now what we claim is that this is linearly independent and it also spans V prime. Okay? So we hope, expect let us first prove so what do we have to do? Let y equal to a1 y1 plus a2 y2 plus etc. an by n, and is such that y is the zero function, linear function. Zero linear function. Then you have y of x equal to 0 for every x belonging to. What is the meaning of that? You have sigma ai yi I running from 1 to n of x equal to 0 for every and which implies this implies by our definition sigma ai yi of xk equal to 0 which implies sigma I equal to 1 to n ai of ai times delta ij 0 for I, j for j belonging to. What does it mean? And that implies y is identity equal to. Okay. So that shows that a linear combination of y1, y2, etc. yn is the zero linear functional implies a1 equal to 0, a2 equal to 0, etc. aj equal to 0, which implies y1 yn form a
So we have proved the linear independence of y1, y2, etc. y2. Now we prove that y1, y2, etc. yn spans So take any y. Let y belong to E. Then y of x, let y of x1 an. Or we can say that ai. Okay. Now we claim, we prove that y is equal to so what do we know y on x1, x2, etc. xn. So let us evaluate this. For a1 y1 plus so by linearity or by usual definition of this, you have I equal to 1 to n ai yi of, and this is equal to sigma ai delta it, and this you know is equal to. So what we have? We have a1 y1 plus a2 y2 plus etc. an yn. Evaluated at x a will give you aj. So if z is defines a1 x1 a1 y1 or y2 that defines then y tilde aj for j equal to that means both y and y tilde take the same values at x1, x2, etc. etc.
y minus y tilde takes the value 0 base k or y is a linear combination of so together these two things consequently what you get y1 y2 etc. is a order basis for so one of the corollaries is that V prime okay, or this is called the dual basis or simply dual basis. So one of the corollaries is that dimensional I don't want to do a proof. I mean, point anything on that. That is what it is. Yes. You have already exhibited a basis with n elements. So this is. So that's about this. Now we shall also need a result. Okay. Which we repeatedly use in several places, so it is better to observe the following. Two different vectors in V. Then the x's a y, a linear functional on V prime such that y of x is different from y of x. So at two different points in V, you can, given two different points in V, you can construct a linear functional, or there exists a linear functional which takes different values at x and x tilde. Now an equivalent formulation of this result is that equivalent if x is not equal to 0 belongs to V, then there exists a y belonging to V prime such that y of x is not equal to 0. Let us prove this theorem. There are two statements given here. So we prove that they are equivalent. And then we complete the proof of the theorem by showing that the second statement is true. So what are the statements? I am doing this elaborately because it forms a sort of opportunity for you to see how one goes about proving certain results. Okay, so the first statement is this: if x and x tilde are such that x different from x tilde, then there exists y belonging to V prime such that y of x is different from y of x tilde. That means there exists a linear functional on V which separates these 2 points in the sense that yx is different from y of x tilde.
The second statement is this. If x is not equal to 0, then there exists a y belonging to B prime such that so we first give the proof of 1 implies 2, and that is what you mean by proving the equivalence. So we prove 1 implies 2. That's the first part. 1 implies 2. Now you see, assume that means x and x tilde are such that x is different from x2. That is, x and x tilde are such that x is different from x2. Let x belongs to B and x is not equal to that's the one that we take here in 2. Okay. Then for any x tilde belonging to B, x and x plus x tilde are different. Because x is not equal to 0. Now by the first statement, there exists y belonging to B prime such that y of x is different from y of x plus x tilde, but y of x plus x tilde, yx x tilde. Consequently, yx is different from let me put it this way. Then x tilde and x tilde plus x are different. Then we have y of x tilde is different from y of x plus x tilde. See, therefore we get y of x tilde is different from y of x plus y of x tilde. That means y of x is not equal to 0. That completes of the equivalent or the implication that 1 implies 2. Now let us take let then we have x is equal to x tilde plus some x star, where x star is not equal to exactly x star is equal to x minus x tilde not equal to. Therefore, by 2 y of x star is not equal to 0, which implies y of not equal to 0, which implies so that is, of course, here this step is this step comes from linearity because y of x minus x tilde is equal to yx minus yx tilde, which is not equal to 0, therefore yx is not equal to. So that completes the proof of. So the equivalents have been the next step is to prove, so we shall prove now statement 2. Here we use a contrapositive argument. Specifically, we show that if y of x equal to 0 for every y belonging to V prime, so this is what you have to show. It's enough to prove this. Okay? So we have to prove this. Let's see how this contrapositive argument we arrive at. Or why do we say that it is enough to prove this? For that, see, suppose we have proved this. Look at this statement. Yx equal to 0 for every y belonging to V prime implies x equal to 0. So what is the negation of this? The negation of this, so what we have is negation of is implied by negation of equal to 0. That is, x not equal to 0 implies the negation of this. The negation of this is what? Yx equal to 0 for every x y belonging to b prime. The negation is that there exists a y, there exists a y belonging to b prime such that yx is not equal to. That's how it goes. That's how it comes. Okay? So it is enough to prove that yx equal to 0 for every y belonging to b prime implies x equal to 0. Now let us do this. It's equal to 0. So let y be the dual basis. That is the basis dual, that is yi Now we take, let x be equal to sigma I equal to 1 to n psi ix, and this is a unique representation of x in terms of the basis. Now yx equal to 0 for every y belonging to b prime. Yx equal to 0 for every x belonging to b, for every y belonging to b prime, implies yix equal to 0 for every yi that is the dual basis. But yix is equal to Try it. Which implies psi I equal to 0 for every I, which implies x equal to 0. So that completes the proof of the result. So this is the proof of the result. Now if you, so what the theorem, see the main, the central thing that we have proved is that you have B here, you have B prime there, and now if you take a Y, you take an X here. Suppose this is your P, symbolically represented by a line. So this is 0 set, this is the 0 element. Now suppose for every Y this maps to 0, for every Y maps to 0. So all these elements map everything to 0. In that case, what we prove is that X is then X is equal to. So, it's a very useful design. Later we shall see that this being repeatedly made use of. Okay. So I think I stop here. Thank you very much.